Hi, what we have today is this. This is the Flir One thermal imaging camera add-on for the iPhone 5 and 5S. This was originally announced in about January at CES. It was a little bit late in coming out, but it's not yet available in the UK and Europe. It was launched in the US around the first week of August, and it seems to be still, I think, shipping out fairly slowly, because there's still, even as of a few days ago, there are a few selling on eBay for about sort of $400 or $500. The normal retail price of this is $350. They originally promised Europe and UK availability mid-August, which has sort of been and gone, so it's anyone's guess when they will actually arrive. This one actually came from US via eBay, so it's probably one of the few that are actually in this country. Now, when this was launched in January, it created quite a lot of press because it was pretty unique. A very low price point for a thermal imaging camera. The entry cost previously was around the sort of $1,000 mark, and so at $350, it's way cheaper than any other thermal imaging camera you could buy. Since it was launched, actually been a few other entrants to the market. I'll just do a very quick summary of those before getting into detail on this. Now, the first one is the Thermap. This is from an Israeli company called Opgal. This is a much higher end device. This has got 384 by 288 pixel resolution. It's much more like a sort of conventional thermal imaging camera. It's got interchangeable lenses and manually focusable lenses. This is designed to go on Android phones. This uses the USB OTG port, which can provide power. So there's no need for an internal battery, so this is just a sort of small unit that clips onto the phone and plugs in. This is aimed more at professional applications. It's a lot more expensive. Now, the next one is the Hammer Imager. This is currently on Kickstarter, and this is based on a sensor from Heimann in Germany. This is actually using a thermopile rather than a microbolometer. I'm not too sure of the exact differences. I think the basic principle is a microbolometer is basically an array of thermistors, whereas a thermopile is an array of thermoelectric generators. One difference they claim is that it doesn't need any flat field compensation to provide absolute temperature indications. This is currently 64 by 62 resolution, but they are claiming that there's a 64 by, I think, 82 resolution sensor due out in December. And this is sort of selling at $250, and this has got Bluetooth and Wi-Fi, so this will support, in principle, iPhones, iPads, Windows, pretty much anything. This does look quite an interesting competitor to the Flir One, if only because of the much wider range of devices that it supports. It remains to be seen how the two will match up, but the specs look pretty similar, so I think that's definitely one worth keeping an eye on. And the final one is very recently announced from a company called Seek Thermal. Very little information. I think they made an announcement about a week ago, which is a strategic announcement since the Flir One became available. They're claiming to have a sensor which is about 32,000 pixels and be some sort of cooperation between Raytheon and Freescale, but there's very little information about this. But they are claiming that they're going to be selling a phone add-on for about $250, so definitely one to keep an eye on, but there's really sort of nothing to see here at the moment. Their website, all it does is just give us your info screen. I suspect they're actually probably at a very early stage, and I'd be quite surprised if we see anything for a while from them. Right, just do a very quick overview on this. Basically, this works as a sort of an external case to the phone. There's this sort of frame that clips over, and I think the idea is that you sort of generally leave this on your phone as a cover. This tips on, it engages. There's a sort of latch there that engages under here, and there's the connector at the bottom. Clicks in like that. It's got its own charge port, and I believe this does in turn charge the iPhone battery. I'm not sure exactly how that works. I've not really looked into the documentation. And the main application. Now, one of the things they've done to save cost is not put an automatic shutter for the non-uniformity correction. Most thermal imagers need a reference field to actually get some temperature calibration. So basically you've got a 3-position switch on the front. You've got off there, that's on, and then to calibrate it you pull it down, and you see it actually pulls a shutter in front of the lens. And when it's running, it prompts you to do that when you start up. You hold it down until it beeps and you feel a bit the buzz of the vibrator in the phone. So if you're using it in a noisy environment, that's mostly needed when you have this spot meter mode for actually doing absolute temperature measurements. If you turn that off when it wants the calibration, instead of having that showing up that symbol in the front, it just shows it in the corner, so it's a bit less annoying, and you can sort of choose to ignore it if you're just really only interested in sort of the general image rather than like absolute temperatures. On the bottom there's a charge LED, and there's also a reset button, which you don't often see on this sort of product. One minor design flaw on this though is you put it down for calibration, and if your finger slips, it actually pings all the way back and goes to the off position, which is a little bit annoying, but I think once you get used to it that won't be a major issue. There's a status LED on the front. One thing I thought was a little bit silly, and I don't really understand, you can actually take this off and it stays switched on. I don't know if it powers down by itself, but it seems a bit silly that you can actually turn it on when it's not attached to the phone, because it wouldn't actually serve any real purpose, but sort of just a minor detail. So it's now prompting us to calibrate. Now the resolution, it's 80 by 60 resolution on the sensor, but they do some sort of extra filtering and blurring, so it looks like sort of quite, you get sort of quite smooth edges, but they're obviously just using software filtering to make it look higher resolution than it otherwise would. Now, and yeah, it gives you basically the sort of functions you'd expect on a thermal imaging camera. You've got various different palettes, you've got sort of monochrome, you've got various rainbow palettes, you've got a high contrast one, so you know, if you've ever used a thermal imaging camera, all this stuff will be fairly familiar. You can do snapshot or movie recording. There's not really a great deal else in terms of setup. It uses the same MSX technology that they have on the E-series, where it combines an edge image from the visible camera. So what you're seeing here, these are edges from a visible image coming from this visible camera there, to overlay it to make it easier to tell what you're actually seeing, because obviously for the low-res thermal image it can actually be a bit difficult to figure out what you're looking at. If I just cover that camera up, you can see it looks sort of fairly... so if you cover that up, you can actually see the native resolution. Now, one thing that's a little bit annoying, obviously this MSX works really nicely, but it really falls over when you start getting really close up. And the thermal image does actually focus quite well, even fairly close up, because it's got sort of fairly small lens on there, but obviously there's quite a substantial shift on the image. And what's annoying is, unlike on the other cameras, you don't seem to be able to turn this overlay off. Now, one thing you can do, you can just if you just sort of cover it up, stick your finger over it, although that hides it, what happens is you then get some noise coming in, because obviously the visible camera is turning its gain up because it can't see any light, so you get this annoying noise over it. The best solution I found to that is, instead of covering up, if you use just something which will let light through in a translucent material, that lets enough light through for the camera not to turn its gain up, is blurry enough that you don't see the edges, so you can actually get a pure thermal image, but it would be nice to have a software option to switch it off. And so here, because we don't have the spot temperature meter, it's just giving us out a little polite reminder to do a recal, but you know, you can still see the images, so the fact the absolute accuracy isn't perfect isn't really a huge deal. But if we turn the spot meter on, it will now get a bit more sort of annoying. Instead of showing the spot temperature, it actually shows the it actually looks like it won't actually let you turn spot mode on until it's calibrated. Yeah, so we've now got the spot temperature measurement. There's not much else in the software. The only other thing is you can turn the light on the front of the iPhone, which is, again, the one disadvantage of the MSX stuff is that it doesn't work in low light, so you can just turn the iPhone's light on there to give you a bit of extra light to help it out. In terms of settings, there's really not much in there. There's just emissivity, where it saves the images, and degrees centigrade or Fahrenheit, so not really a great deal to play with. And I think that certainly I'd have liked to have seen an option to turn off the MSX, as well as the basic applications. A few other apps that they've done. One is a close-up. Now, the idea behind this is that it lets you actually adjust the offset for the MSX. The problem is this doesn't give you enough adjustment range, although it works okay if you want to get into real close-up, something like components. Although the camera will resolve it reasonably well, this application doesn't actually give you quite enough shift range to actually get it close enough, so that's something they could really do with tweaking. Although the problem is when you get close, it becomes very sensitive to distance. It's sort of limited use, but I mean, for looking for hotspots on PCBs, unfortunately this horrible iPhone screen is so reflective, it's picking up the overhead light quite a lot. But yeah, that hotspot is a SOT23. Some of this bobbiness is just because it's doing the upsampling from the fairly low res display, but it is sort of viable for looking for hotspots and so on components. Right, so let's take a look inside. It uses some very small security Torx. Right, so we're just sort of seeing the back of stuff at the moment. That's just the connector into the bottom of the iPhone, and just a flex going down here. Fairly big lithium ion battery, which is 1400 milliamp hours. Flex and a bit of copper shielding tape. You can see the back of the sensor connector there, and everything else is underneath the board. Let's take a look. Good to see lots and lots of test points, which should be interesting to have a poke around at. There's not much on this little bottom board, just the connector. There's a little 8-pin chip there. I'm not sure whether that's to do with charging or whether that's the evil Apple chip. Right, we've got a rather fragile looking flex to the front. I'm sure that's going to be for this front switch. Let me unplug the battery. Right, now I've got this out, I can see what this is. This is the front shutter assembly here. So this chip here is going to be a temperature sensor that's measuring the temperature of this shutter to give it its reference. And this front is actually aluminium. The rest is all plastic, but this is aluminium. So you get the temperature is going to be reasonably equal between the sensor and the place it's looking at. One thing that's a little bit interesting is there is actually a window on over the thermal camera. It's not. Yeah, it's not completely clear, which is a little bit surprising. Obviously that gives a little bit of protection, but not sure what material that is. It looks sort of visually completely opaque, maybe silicone or something. So obviously there aren't many materials that are transparent to far infrared, so I'm a little bit surprised there's actually a window on there, which is probably going to be attenuating the infrared to some extent. It could be that might be doing some visible light blocking, but so that's just the temperature sensor and the switches. There's two little buttons on the PCB that are detecting the switch position down there. Right, so let's take a close look at what's in this PCB. We've got the main processor here. This is an Atmel 1891 SAM 9X25 ARM processor. Next to it there's a Micron dual RAM and NAND flash chip. It's got 128MB of flash and 64MB of DRAM. Got the two camera modules here. This is the visible camera module with a flat flex connector, and this is the thermal sensor. This is really the heart of this whole thing. This is the new Flir Lepton thermal imaging core, which we'll take a more detailed look at in a minute. Down here there's a Sonix SN9C270. This is a camera to USB control, so this is interfacing the video camera to USB. I'm not totally sure whether it's interfacing that camera directly to the iPhone's USB, or maybe it's actually we've got some of the image combination between the visible and the thermals being done on here and being fed through the camera interface. Not really sure about that. That's an SPI flash chip that's holding firmware for this camera control chip. Not a huge amount else. This is obviously some sort of power chip. We've got this inductor next to it, and the rest is all sort of fairly small stuff. I'm guessing these are just various regulators to support the thermal imager, which probably needs sort of various supply voltages. There's two little switches here which sense the position of the front switch. That's the connection to the battery. That's probably the either regulator or charge control chip. This little chip here next to the ribbon that goes down to the USB, and that's really about it. And there's no components at all on the other side. You can see the back of the thermal imager socket here. So it looks, unfortunately, there's quite a lot of glue around these camera lenses, which could be a bit of a pain. But so here we go. If we just unclip that camera. Right, this unclips, that's the camera socket, and this is the back of the, this is what they call the Lepton, which is their new low-end thermal imaging camera core, which is a massive investment by Flir to miniaturise a thermal camera down to the size of a mobile phone camera package. Right, if we peel that ladle off, you can just see there's a chip on the back of there. This looks like a sort of ceramic hybrid type assembly. So unfortunately it looks like this lens is glued into the top of this, so you might need to try and get that off. Right, this glue looks like it's vaguely soft. I think it might be feasible to cut it away without causing any damage. I'm going to have to do this under my magnifier. Yeah, this glue looks like it's coming off quite easily. It's not bonded too heavily to the plastic, so hopefully we should be able to peel it off. Yeah, there we go. That's a lot easier than it could have been. So, this is where the magic happens. So this is the Lepton camera module. These contacts are on the front. This is for situations where you've got a mechanical shutter in front, and these make contact with the shutter assembly, so they can do a module with a built-in shutter and have the connections on there. Now, there is some glue holding this lens in place, but again that seems to be fairly soft, so I think you might actually be able to unscrew the lens. Okay, it might be interesting getting it focused again, but see. So it's not really a great deal to see there. You can just see the surface of the sensor, but at least, yeah, there's probably scope for using alternate lenses on this. If we can actually get this lens off, there's a reasonable size aperture that we could probably get access for a different lens if we wanted to. And looks like we've got the front element here, but there's also a square piece on the back. I'm guessing that's probably going to be some sort of filter, maybe a filter to block visible light. Can't see a huge amount in here. We can just about see the edge of the sensor die, and also looks like there's some shielding on the inside. So I think what we're actually seeing there is the reflection of the contact pads in the shielding of on the side. So this is sort of looks like it's soldered down. It's either soldered or conductive epoxy down onto the top. So these connections will be these top contacts, and the shield. So I mean, if you're using this with another lens, I think you possibly could actually take this top plastic off, but I'm not going to do that. Yeah, actually looking at these joints, looking at that little streak there and the general texture, I'm pretty sure that's going to be conductive epoxy, and also because this is plastic, you don't really want to be soldering that. It would distort it, so I think that's just been put on there with conductive epoxy to give both the electrical and the mechanical fixing of this top lens holder assembly to this ceramic hybrid underneath. Interesting little array of test pads there. Those might be interesting to probe at some point. Might need a bit of interesting test jiggery to be able to get access, but might be worth a play. Now, of course, what we'd really like to be able to do is actually run this camera module without it being attached to this piece of Apple junk. Now, fortunately, the way this board's laid out, we can get access to the pins quite easily, and the way this flex is laid out, we should be able to have it all plugged up together and running open fairly simply. So let's go. Okay, so we've got this all set up so we can start having a probe around. I've just stuck most of the bits down to a bit of fiberglass board, because things like this flex are quite fragile, so I don't want those breaking. And this bit of PCB here is just resting on the switch to make it think that the front switch is turned on, and then we've got access for the calibration button there for when it wants to be calibrated. Before we get too stuck into here, let's just see what we can find to help us with this investigation. Right, so around this time, the time this was announced, I did a bit of digging to see if I can find some patents with anything interesting. This is the first one I came up with, infrared system housing, and this is basically talking about just the packaging and in particular the shielding of it. It does include some quite interesting images. So we can actually see sort of the sensor in its socket here. There's a few slight variations on this, but also how the sensor is packaged with its processing electronics to form a sort of single module. And here we can just see some detail showing the actual sensor with a sort of BGA type attachment to a substrate, and then the processing chip bonded onto the rear. And there's another version here which is the more sort of what you tend to see cameras nowadays as a flat flex module rather than a socketed module. This version shows some metallized contacts on the front. We can see what these are for in this image here, where it's showing like a shutter module that sits on the top, and those are providing contacts to a shutter for the non-uniform correction for accurate temperature measurements. This was back in 2013, so this was covering probably a few of the packaging options they were exploring at the time. This second one has got quite a lot more information in it, and this sort of just shows a generic system of a sensor with processor and display, etc. And again, we've got these assembly pictures. There's quite a lot of overlap between the patents. This is the actual sensor array where we've got the amplifiers, and this goes into quite a lot of detail on the shutterless non-uniform correction algorithms, which basically these rely on the fact that the thing is moving, so that because you've not got a static image, if the thing is moving, then the average of a small cluster of pixels is going to be fairly similar, so that any pixels that stand out on a sort of time average of that are likely to be ones that need a bit of correction. I've not looked into too much detail. You can read this if you want to get into the details, but sort of the general idea is the fact this thing is on a phone or on a handheld device means that you can make some assumptions about the content, potentially with the assistance of an accelerometer. It's not clear whether it's actually using the accelerometer or not, but the fact the image is changing means that you can make some assumptions about average intensity levels and then use that to apply some local corrections. And here we can see a little bit more sort of the general principle here. Again, we've got some image change detection here and sort of various filtering functions, and also showing that some of the functions work at full frame rate and some every 32 frames. So it's obviously doing sort of this sort of blur average here, which is working on the assumption that the image has moved within that period. And that the average pixel intensity is going to be fairly similar because of the motion blur. Interesting, there's a thing that's there that says access is block RAM, which might possibly give a hint that it's designed to be running an FPGA. Whether that's meaningful or not, it's a slightly interesting sort of form of words to use on a diagram like that. And here we can actually see it as part of a phone type package. Again, this is an early version showing sort of a different layout to the one we finally see, with a quite a lot significantly bigger lens. And there's a few interesting little snippets in the text here. There's a few different resolutions mentioned. It says less than 160 by 120, and there's a few other resolutions mentioned. So again, they may be planning some sort of different variants. One interesting thing here is the some discussion about frame rates. And again, this mentions the technique they use on the E4 of using a high capture frame rate to average down to reduce display frame rate to reduce noise. So for example, here we've got 2 frame rates. Approximately it says sort of 32, 60 Hertz with reduced noise compared to the original image. And in fact, even some of the it's even mentioning the RIC is the readout IC, which can provide data up to between 120 and 480 Hertz. So again, that's probably using multiple frames and then doing frame averaging to reduce the noise, so they can use a smaller, cheaper lens. And again, it goes into here about the using the motion blur to provide non-uniformity correction data. And this does actually specifically mention using FPGAs for processing, or it does also mention ASICs as well. Again, they're just sort of covering bases. Right, so this is a data brief from the Flir website. I'd hardly expect to find a full data sheet, but there's actually a lot of very useful information here that's going to save a lot of time in trying to figure out the interface and the other details. So the first sort of interesting thing is this, which is saying basically integrated digital image processing, which basically appears to do pretty much everything: noise filtering, non-uniformity correction, gain control. According to this, it looks like this produces a pretty much ready-to-go image, which is obviously nice. Less than 9 frames per second frame rate for export control reasons, which is not surprising. This is an interesting one: MIPI interface as well as SPI. Now, MIPI is the interface which is used by mobile phone peripherals. Obviously, they're designing this so it can interface to a mobile phone interface on the camera. 2Y I2C like serial control interface. Well, yeah, we know what that means. Lots of manufacturers do that. They just don't call it I2C because of the licensing issues, but it's basically the same thing. Power supplies. This is again very useful information. The 2.8 volt sensor supply, a 1.2 volt core supply, and an I/O voltage from 2.5 to 3.1. Now, 3.1 is interesting. Why wouldn't they go up to 3.3? Seems a little bit odd. I wonder if maybe they're using, you know, a fairly small chip geometry that just doesn't quite let it go to 3.3. Seems like a slightly odd omission, not going all that the way up to that voltage, but obviously as chip geometry's voltage does start to become a problem. Fast first image time, half a second. That's maybe some stabilization time. Gives some power information. Now this is very interesting: 32-pin socket to standard Molex or similar side contact connector. Now, just literally knowing this was 32-pin Molex connector, it didn't take me long to actually find out the exact connector that it was using, which matches up with all the drawings in the patents and everything, which is this. This is designed for, a while ago it was quite common for mobile phone cameras to actually go into sockets. Now they pretty much all sit on flat flex cables. Needless to say, this has got a sort of stupid minimum order quantity and there's no stock anywhere, but I did find something very interesting. It's listed in Mouser and they've got some on order due in October. Now, I wonder if that's because, you know, someone that's in the Lepton, a Lepton developer has persuaded Mouser to stock them, or maybe perhaps Flir are actually planning to offer this module through Mouser, which I think would be extremely exciting if that was the case. But the socket looks like it's potentially available, which is good. I have actually figured out a way of making a socket in the meantime, which I'll go into in a minute. So back to this data sheet. So we've got the basic block diagram here. We've got this CCI, which is basically I2C configuration interface. We've got what they call video over SPI, so that's a video interface, or MIPI, and we've got our supply voltages, and we've got a master clock. Another interesting thing is here, the MIPI, it says feature anticipated in a future product release. Now, again, that suggests to me that this may well have an FPGA in it rather than a custom chip. Obviously, if they're designing a custom chip, that's a huge investment, so they're going to try and get everything in there from day one. And it's possible they've got a custom chip and the MIPI bit didn't work and they're doing another revision, but it's also possible that they're actually using an FPGA, which I think would make a lot of sense because this is a very new product in, there's probably all sorts of new markets they probably haven't even thought of. So to have the flexibility of having maybe stuff in there for, say, gesture recognition, occupancy sensing, and maybe to have a high frame rate version for use with a different lens, because I would imagine some applications of things like firefighting, search and rescue, where you need a greater than 9 frames per second frame rate. So I'd be highly surprised if they spent this much development on this sensor and not have some capability to do high frame rates for the applications that need it, say potentially with a larger lens and different FPGA code. But also, if this thing's got non-volatile FPGA code, that would be quite a nice way of locking down the frame rate to get around all the export control issues, so they can ship something knowing that the frame rate is sort of fairly well nailed down and not have to worry too much about that, and they can ship the high frame rate ones under the export controls as a completely different product. So here we've got some, just again, pretty much the specs. They've got the shutterless automatic non-uniformity correction. Again, they specifically mentioned with scene motion, so basically they're saying, as long as it's moving, then it will do automatic non-uniformity correction, but it will also support the use of an external shutter. And again, image optimization. Again, that's another reason why you probably wouldn't expect this all to be nailed into an ASIC, because there's so many parameters that they might want to tweak on this for different applications. I think unless it's a very flexible ASIC, I think an FPGA is probably a more likely thing, at least, you know, for the first few 100,000 or so. This is also interesting. This gives information about the input. So we've got 14-bit, which will be basically the raw analog data. 8-bit with automatic gain control, so that will be for, you know, vision type applications where you don't care about absolute temperature, but, you know, you just want a visible picture showing decent contrast. And also 24-bit RGB, so this will be the classic sort of thermal image colour palette modes with the colorization already done for you. So, you know, it really looks like this thing will literally, you know, give you RGB straight to display with almost no additional processing, which is obviously very, very nice, because there's a huge amount of processing that you need to do to get decent images out. And if that's all on chip, then this is, you know, very nice. If it's actually on chip and not buried in the iPhone app, for example. A few more bits here. 25 megahertz input clock. A little bit surprised it's that high. I would have thought, you know, it might be nice if they'd used an onboard PLL so you don't have to deal with the high frequencies externally, but it's not ridiculously high. Video SPI, video interface that we've seen, and our voltages. Power dissipation 150 milliwatts, so I'm guessing that's going to be of the order of, say, from a 3.6 volt supply, you're going to be talking about 50 milliamps or thereabouts. There was an interesting little thing here, the operating power. Well, it says 150 milliwatts, but then below 190 milliwatts over the temperature range. So I wonder if at low temperatures there's some heating, like they do on the E4. They actually heat the sensor to get a consistent temperature. So that's a little bit peculiar, the fact they say that over temperature range. So yeah, maybe there's some active temperature control going on. And again, this is also quite a nice little diagram, which basically this tells us what almost all of the pins do. All we've got to do is figure out which one is which, basically. So we've got our main supply 2.8 volts, VDD for the I/O voltages 2.5 to 3.1, core voltage 1.2, and again, that, you know, if this has got an FPGA in it, then 1.2 volts is an extremely common core voltage for an FPGA. Power down. The other thing that caught my attention is the power down current consumption. They say 4 milliwatts. Now, if this was an ASIC, I would have thought they'd be able to get the standby power down less than that. So again, that would suggest to me this is probably an FPGA that has some power down capability, but they quite often don't go like down to like stupidly low power. But they just go into a much lower than a normal FPGA power draw. And so we've got the currently unused MIPI outputs, our I2C in inverted commas, similar to I2C, and our video over SPI, which has got exactly what we'd expect, with, you know, the chip select clock, data in, data out, and some I/O, which I'm guessing they just basically used the spare I/O pins, sort of the spare pins, just to provide some I/O for where you've got a sensor that needs a little small amount of I/O, for example, for controlling a shutter. We've got our dimensions, which again, this confirms that Molex socket, because the dimensions are identical. Right, now obviously the first thing to do when trying to figure out an unknown pin out is find the grounds. A number of reasons for that. One is it's probably the pin that there's going to be the most of. It's also the easiest one to find on the PCB. You know, we're going to have all sorts of places that are going to be very obviously ground, like for example a negative battery terminal. One thing that I was rather surprised wasn't grounded though was this frame. This actually appears to be completely isolated from everything else, which seems a little bit odd, but we've got these mounting screws here, and I've just got the meter set up on continuity mode, so I've disconnected the battery so we've got no sources of power to confuse anything. So I'm just going to literally probe each pin in turn to find out which one shows continuity to ground. When you're doing this, it's important is don't just go by the beep, just always check the actual reading on the meter, because you might find something that's got a sort of low resistance to ground that isn't actually directly connected. So whenever you get something you think is ground, just double check on the meter. So it looks like we've got 3 on that bottom row. Obviously on a device like this, some of these may be analog and some digital grounds, but generally, you know, they tend to get connected together externally, so it doesn't really matter too much. Right, so we've got 11 pins connected to the ground out of the 32. So the nice thing is, you know, any pin that we know is a ground, we know isn't something else that we've got to figure out. Now, of course, some of these might not be ground pins, they might be test pins or something, but, you know, we don't really care about that if we're just trying to get this thing running and figure out what's going on with it. Just really need to replicate what's going on here. So after the ground, the next thing to look for is power. Now, the first clue is to look for things like pins connected to capacitors, but also wide tracks on pins are also a big clue that it's a power pin. And here's a really good example of a pin which is very obviously a power pin. We've got ground either side of it, a couple of decoupling caps and a nice fat track. So you know, this is absolutely going to be a power pin. I've just measured this, and this measures 2.8 volts, so that's probably the analog core power supply. And obviously just going around with a scope, you know, looking for static waveforms, but obviously looking for common voltages. You know, we already know that we're looking for 1.2 and 2.8 volts, and a core voltage that's somewhere between 2.5 and 3.1 volts. So we should be able to find those. But also the fact we've got these look pretty much like voltage regulators around here. I'm guessing these are probably going to be their power supplies. So power supplies are probably going to be coming on this side of the chip. Right, I'm not going to go through all this on video because it's just too much of a pain with the camera in the way. I'm just going to go through it, but say the next thing I'm going to do is check for supply voltages and then go around all the pins of the scope and see if I can figure out which pins are which. Right, found a few interesting things. This is clearly our 25 megahertz clock. 4 pins surrounded by grounds sitting at 1.2. I'm guessing those are probably going to be the MIPI outputs. I can't see any tracks coming from them outward from the socket, and if I actually come to think it, there's actually a hole in the board under the socket, so I think pretty much all the used tracks are going to come out, so I'm pretty sure those 4 are probably going to be the unused MIPI or possibly GPIO pins. I found all the supply voltages as 1.2, 2.8 and also 3. There's quite a few pins at 3.1, so I'm guessing one of those will be the IO supply, but the other 2 or 3 are probably control inputs, like for example the reset and low power inputs. When you look at this sort of thing, if you find, you know, you can generally figure out which one is a power pin, and any pins that are at the same voltage, a quick check is to power it down and do a continuity check to see if they're additional power pins or if they may be coming from a logic supply. Another trick is just use like a low value resistor, like a 100 ohm resistor or something, and just try pulling the ground and see if they move. So if they're logic pins, then they'll droop down a little bit, so you know those are control pins. Right, down here I think we've found the SPI interface. Now these are, I think this is either a framed chip select or a data in. Just looking at the time, that's about half a microsecond period. So let's have a look at some of the pins. And the other thing is, almost always you'll find your interfaces, the pins are grouped together, so you know all the SPI pins are almost certainly going to be next to each other. This is going to be our SPI clock, almost certainly. We've got a lot of overshoot because I haven't got a proper ground. I've just got a scope ground lead. I haven't got a low impedance ground on this, but this I'm pretty certain is going to be our SPI. So that's being clocked 16.6 megahertz, which is a fairly plausible speed. We can see it we've got these groups of 8 bits. Right, we've got a lot of transitions on this, so I'm thinking that's probably going to be the data out. The problem is this seems to be being read at a fairly sort of random time. There doesn't seem to be any really nice sort of clean time base on here. The other thing that suggests it's data out, as we can see between the bursts, we've got this fall off, so this is where it's tri-stating, so that's, you know, outputting the data and then the bus is going into tri-state. It's interesting, we've got these sort of fairly arbitrary looking groups rather than a nice sort of steady burst. That may just be because of, you know, whatever the processor is dealing with. Yeah, we don't really seem to have much in the way of sort of either line or frame structure here. It's all sort of fairly random, which doesn't really help. Yeah, timing is quite often a very useful aid when you're doing this sort of thing, but we don't really seem to have that helping us very much. Right, so and that's one I suspect is probably data in, and this I think is data out, just looking at all the randomness on it. Not sure if we can get this stable enough to actually see any difference when I sort of wave my finger in front of it, particularly. The reading just isn't stable enough, but I mean that looks random enough to be output data from the sensor. And yeah, I think this looks like chips. Like I'll need to solder some wires on so we can see all these simultaneously. But we've got a similar sort of bursty structure of the chip select being low for a sort of relatively long period of time. You know, around the sort of 100 microsecond mark. So we've identified these are definitely our SPI pins. And on this pin that looks like data in, I haven't seen it send anything other than zeros, which is good, so it means we probably don't actually have to send it anything down the SPI. We just throw clocks at it and it spits the data out with a bit of luck, so that's probably one less complication we have to deal with. Right, and over here this looks like I2C. We've got about a sort of 2 microsecond period. We've got this slow rise caused by the resistive pull-up on the I2C bus, so that looks like our SCL clock line because it's fairly regular. And next door to it, this will be our SDA line, so again I'll hook some wires into this so we can then dump the actual I2C data. So that's identified sort of the major things. I just need to go around and sort of double check all the static pins to figure out which ones are power supplies and which ones are logic control. But I think we've figured out most of it. Fortunately, that data brief gave us a huge amount of the information that we needed, so that solved a lot of the problems. It was really a case of figuring out which pin was which. Right, just a couple of pins I'm not totally sure about. I thought these were probably the power down and reset pins, but it seems to have some weird sort of bursty sort of signals on them, only at startup. It could be those are perhaps the GPIO pins outputting some sort of debug information or something, but again I think I need to get a proper probe set up to look at these in more detail. Right, so we've got most of the pins figured out, certainly enough to get stuck into looking at what data is going in and out of this thing. I'm going to leave the details of that for the next video, so I want to get this edited and out, and then just get stuck into some more serious analysis fairly soon over the next day or two.